So in this video we just want to see how many comparisons our bubble sort will use and how we could reduce it slightly. We looked in the last video and talked about the big O notation for this, and we were looking at it being n squared, so whatever the input size is, number of comparisons being n, the length of that, so n times n. And that's because of that nested for loop. So one for loop going around n amount of times and another for loop going around n amount of times. And it doesn't quite end up being n because we do subtract 1 every time, because on the very last item in our array we don't need to check it against nothing. We don't need to check it against the end point. So we will end up with less than n squared amount, but that's because we don't need to compare the last item to nothing. So if we do it for, let's say, 1,000 integers, we'd expect that the bubble sort here would go around roughly around 1,000,000 times, but if we're subtracting 1 for every 1,000, so a million minus 1,000, possibly 1,000,000 minus 1,000, because each one of these outer loops has this inner loop which is the same length but minus 1. So if we were to try to kind of write it down, we would have it'd be n for the outer loop, because it's going around the length of the array, times by n minus 1. So it'd be, essentially, it would equal n squared n to the power 2 minus n. Because for every single one of these, it has one less in the inner loop. But you don't have to worry about that too much, because actually, for us in big O notation, we're only bothered about the way it tends. So we could have minus whatever you want here, but as long as this is like a linear n, it's really not going to affect the shape of the graph. The graph is going to be a polynomial, and it's going to be the n squared that's really affecting the time complexity here. So we would still refer to this this subroutine as being n squared efficient, even though it's not exactly true. So if we have 1,000 items, then if we have 1,000 items, so n would be 1,000. So 1,000 times by 1,000 minus 1, and then that will give us 1,000 times 999. So we expect it to go around with 1,000 as n, we'd expect it to go around 999,000 times. So we're going to prove that by just making like a counter. Set it to 0 initially, and then inside the inner for loop, that's where it's doing its comparisons, its operations. Count plus to increment, and then at the end of our outer for loop we can output how many operations. So I can just type number of operations and then concatenate that with the count that we've created. So if we run this, we expect it to output unsorted, then output the whole array so we can see it. Output the word sorted, then the bubble sort, it will do it itself, outputting number of operations, before then outputting the sorted array so we can see it. So that's with an input set of 1000. Okay, so we got the unsorted list, there's 1000, and they are unsorted. We can see that because it starts at 6033, and down here there's a 365. So yeah, very much unsorted here. Then we have our sorted, and our operations end up being as we calculated. So it took 999,000 operations for it to do this sort. But that's a bit of an excessive amount. So what I'm going to do, we can do some things to sort of reduce this. So I'm going to copy my bubble sort. Let's copy the whole subroutine and paste it in here, and I'm going to name it bubble sort no swaps. So in this one we're going to edit it so that actually when it gets to the point where it's going through and it potentially makes no swaps, we don't need to carry on going around the for loops. So we did see it in the last video when we had an input set and an array that was nearly sorted, or it could in fact be an array that is actually sorted. If you just put it through this bubble sort, it would still take n squared, roughly, remember, n squared amount of times. But we could simplify that and say if it doesn't actually make any swaps, so on this inner loop, if we end up not making any swaps, then we're sorted already. So we don't need to carry on. So that's what we're also going to do here. So we're going to leave the count in there, but also introduce a new variable called swaps, or swap. In fact, we're going to introduce it into the outer for loop. So Boolean data type, swap, and set it to false. And then if we do actually end up swapping, swap, you can set to true. And then outside of that if statement, and in fact outside of the inner for loop, so if we've made a swap, then what we can do is say if swap break. So what that's going to do is if a swap has been made on this inner for loop, so we are still actually changing and sorting our list, but it's not going to do this if statement because this is, I've wrote here not swap. So swap would be true if we have made a swap along the way. If we haven't got any swaps, break. Now break's just a keyword that allows us to break out of a particular programming structure. So in this case, you see when I highlight it, it links up to the for loop. So when it gets to this point in the code, it will break out of that for loop rather than continuing with the set amount that it had. So that for loop was due to go around, let's say, 1,000 times, and on the 50th time it's actually not made any swaps, so it's all in order. We can break out that for loop and it will just jump to the end. So this one, in comparison to this one, this is going to go around and try and sort the whole list even if it's in order already, or nearly in order and it only needs 1, 2, 3 changes, or a smaller amount of changes than the length of the list, it's just going to keep going. If we sent in a sorted array to this one, it would check it and go through it once, go through all of them, checking the pairs of numbers against each other, and if a swap has been made, it will carry on round. If a swap hasn't been made, we can stop. It's already in a sorted order. So what we're going to do is try and compare those two, see how we get on. So int. So we're going to make a new int array. Obviously, we need to compare them with the same values, or else it won't work. So I'm going to call it ns for no swap. I'm going to write no swap. So this is my integer array for no swap, and I'm going to just take a copy of the int array. Array dot copy int. Okay, so I need to declare it first. I'm going to copy it into the destination one. Is going to be the int array no swap, and the length is, well, it's the same length as the original array. Unassigned, yeah, I need to make an instance of it. New integer array of length, int array dot length. So let's sum up what I've done here. So we already had our integer array being randomly generated. So 1,000 numbers would be put into this integer array. I then needed to make another one, so I would be able to do another sort and compare it with the same data. So made a new integer array of the same size, and then I've copied that one into that one, and you need to specify how many, the total elements of the array that you're going to be copying in. So if you're ever stuck with this stuff, you can actually just read what is going on. So yeah, the source array, the destination array. So it copies a range of elements, starting at the first element, passing them into another one. So we've copied it. So we've got, if we put a breakpoint after that, I should be able to prove to you that the arrays are identical. Do that. So it starts the int no swap array. You can see down here, starts at 8,028, 9,077, and we look at the int array, it's got exactly the same. We could, of course, use something that we saw the other day as well, and calling the random array ints, but use a seed value rather than let it use the system time. So we could put a seed value in there, 1001, and then both, although we're calling the random generation of these two arrays, they both get the same. And I hope you went and read that article about the man who rigged the American lottery. He did it using pseudo-random numbers like we discussed in the last video. So this also will get us identical arrays. There's lots of different ways of doing these things, and we'll just prove that before we move on. So we'll have a look inside of int array. An int array contains 6,739, 5,293, and we look at int this one, and it's exactly the same. Exactly the same. So if we go down to the end, we have a look. It ends in 96, 4,000, 2,507, and we get the same ending down here. Okay, so we're going to leave it at this one. So we've got these two arrays that are identical. We now, I think we're trusting that the arrays are actually being sorted, so I'm not going to bother to output the arrays now. But I'm going to change this label to sorting standard bubble, and then we're going to say have a label saying sorted no swap bubble, and we're going to call it so bubble bubble sort no swaps, and we're going to send in the integer array that we just made there, so no swap. The reason we're sending this one and not this one is because after we've done the bubble sort, it's already sorted this one, so it would actually take only 1,000 comparisons because we've been doing 1,000. But I suppose we could show that. We'll show that after. So we're looking at the same array, the same initial array, and seeing whether our no swaps one will have less comparisons in it. Have a look as we go. Okay, so to sort using the standard bubble, it took that same amount, and it's going to take that same amount every single time. To sort the one where we stop actually sorting when we've actually run through the pairs, comparing pairs of values every single time, and not making a swap, we've actually reduced our operations by a significant amount. You know, if each operation was taking a millisecond, we're saving nearly 10 seconds, possibly more than 10 seconds, if that was the case. Okay, and what we'll do as well, we'll run it, we'll copy it again, sorted no swap bubble, sorted no swap bubble with sorted list. So this will show you, start from the top. So we've got our sorted list, sorted standard bubble. So it would do. This will do it again 999,000 times. The no swap will do it less because once it's sorted, it doesn't carry on and keep checking. And this one, well, this is going to be trying to sort a list that's already sorted. So what this one should do is just go through 99 times, because we wouldn't check the last position. That's what I'm going to estimate. It should go around 99 times, and because it didn't make any swaps, it's already sorted, so efficiency, brilliant. Or much better efficiency than putting it through the standard bubble. So yeah, it came out with my estimate. So with a sorted list, it goes through and checks pairs. If it didn't make any swaps, it can just leave it there. It doesn't have to go around again. If we put a sorted list into the standard bubble, I might as well show it. It's going to still do it that same amount of times. Because it doesn't check to see whether it's already in order or not. It just continues going round and round and round. So even though the list is already sorted, it's still to get that many operations. We can reduce this stuff even further, however. When we are sorting a list, let's say it was this list, 2, 4, 1, 3. So the first time it goes around and looks at the pairs of them, there'd be no swaps there. Those two would swap, and then the 4 and the 3 would swap. So we'd end up with a list of 2, 1, 3, and 4. Now, the next time we go around, using the standard bubble sorts that we've been doing, we would swap those two. So it'd be 1, and then 2 would be there. So the 2 and the 3 would then remain where they are. So 2 and then 3. And it would still compare 3 to 4. Now, when we're checking when we're comparing our pairs, each time we're just picking up the highest value and pushing it to the right. So actually, we don't need to do this comparison in this case. I'll show you again where I've done it completely reverse order, so you can see what I mean. So that's in descending order, and we were doing a bubble sort to do it in ascending order. Those two would compare and they would swap. The 3 would be there. The 4 would then compare with the 2 and they would swap. So there'd be a 2 there. And then the 4 would compare with the 1 and the 1 would be there, and then the 4 here. The next time it went round, it would be pushing the next highest number to the right hand side. So the 3 compares with the 2, swaps. The 3 compares with the 1, swap. The 3 compares with the 4. Now you don't have to do that 3 comparing with 4. That's what I'm trying to explain to you. That you don't need to do this last comparison, because you know the first time you've gone through, that highest value is already in the correct position. So we're going to make another one based on the no swaps bubble sort. I'm going to make another bubble sort, and we're just going to try and shave off some more comparisons. Just by making a little change to it. So I'm going to change the name to bubble sort no swaps, less comparisons. It's a terrible name. Less comparisons. And how I'm going to do the less comparisons is, at first, this outer for loop is going to make sure it goes through. It's going to go through it wants this inner for loop to go through the entire array. When k is 1, we know that the last position isn't going to be important to us anymore. So if we take k off, that's going to take another 1 off the array length, so we don't need to check that extra 1. The next time it goes round, we'll have got the second highest one to the end. So k becomes 2. The third time k becomes 2, so then we're not checking that last one, that last x amount every single time. So we can still get a sorted list but the comparisons are going to be far fewer. So we're going to do one more of these. So we're going to make a new array here with the exact same values as in the other two, no swap, and we're just going to say LC for less comparisons. And we're going to do the same thing down here, no swap with less comparisons, no swap bubble less comparisons, and integer no swap less comparisons. And just to prove to you that that one actually does do the sort as well, we'll do the output for that particular array, less comparisons. Okay, so we're sorting with a standard bubble. We expect it to get us 999,000. We do it with a sorted list. We expect it to get 999,000. We do it with our no swap checker, and we expect less to be checked because once it's actually in order, it doesn't need to keep swapping. The only time that this would be the exact same length as the regular bubble sort is if they were completely the wrong way around. So if we were taking something from ascending to descending or descending to ascending. And then the same thing with a sorted list where it actually only goes around once because we are not interested in carrying on if we haven't made a swap. And then this last one with less checks, because as we push the items to the right hand side, we don't need to check those anymore. We know that if they've got to the right hand side, they are the biggest numbers or the smallest, depending on which way around we put the less than or greater than sign. So we should see the least number on the unsorted array on the less comparisons one we just made. So let's have a look. In the end, it ended up being the same as the no swap bubble. So that's something to look into as to why that's happened. Oh, it's because I haven't actually called it. I've just called the null swaps. That's why you have to be careful when you just copy and paste. Bubble sort, no swaps, less comparisons. Here we go. I knew it shouldn't have been the same amount of comparisons. Yeah, so a significant amount less, in fact, almost half the amount. But we would still classify this. We will still classify this less comparisons one as being n squared. And we'll see more when we cover a big O in more depth.